Hello and welcome back. Further maths today, enrichment, one of my favorite topics, which is series. We're going to be finding the sum to infinity of a very special series. I'm going to write it down in explicit form. It starts with 1 over 1. The signs alternate, and we're going to have 1 plus 4. So, can you guess the next term? 1 plus 4 plus 9. Now we go back into minus, and we're going to have on the next denominator 1 plus 4 plus 9 plus 16 with a 1. And let's write one more term. So we're trying to find the sum to infinity of this. Where do we start with something like that is the question. Okay. It doesn't fall to any category. We shouldn't really be looking for perhaps anything geometric. It's not something I recognize as a standard Maclaurin, perhaps with a suitable substitution. But this is something quite special. I mean, it's quite clearly adding. If you look at just at the denominators in their own right, I'm thinking of the sum of r squared, which of course is a very standard formula from further maths. So my first thought when I look at this is to write it in standard sigma notation, and because I'm going to need a lot of the board today for some of the workings, I'm going to actually write it on the top left up there. So I'm going to try to condense this. So how can we write all of this? Well, quite clearly, let me just write it here and then I'll transfer it in there. This quantity here is of course the denominator, the general term for any of these denominators. So if we start from r is equal to 1 to n, so on the fifth term, let's say 1, 2, 3, 4, 5, it should be when n is equal to 5, it should be of course 1 plus 4 plus 9 plus 16 plus 25, but that's of course on the denominator. So I need to write it bizarrely as 1 over that. And very poor choice of where I've done this on the board. Let me rewrite it again, a little bit lower perhaps. So I'm going to write it as 1 over the sigma from r is equal to 1 to n of r squared. So this is now a term like this. Of course, we need to add afterwards this term. So it's got to be another sigma, a big sigma on the outside. So this obviously will start with n is equal to 1. Let me just write it and then we'll just check that it does work. And of course we need the alternating quantity. Very easy to produce that. It's going to be minus 1 to the power, is it n or n plus 1? So we're getting the right sign on the first term. In order to get a positive, when we're putting n is equal to 1, this will go of course negative, so let's put n plus 1. We can of course put n minus 1, it's the same thing. So let's just check, for example, if this is the correct thing. So let's say we wanted to just add these 5 terms, not to infinity, so this will be obviously 5 there. It says add alternating terms whose denominator is like this from n is equal to 1 to 5. So we're going to be adding, when we're putting there 1 for our n, we're going to put there 1 squared, which is just simply 1. This will go positive, so that will produce of course a 1. When we put there now n is equal to 2 there, this will go negative because this will, of course will go to the power of 3, and then of course 2 there, we'll be adding of course 1 over, and now we're going to have r squared up to 2, so it's going to be 1 plus 4. Then if we're putting now n is equal to 3, that's going to go positive, so this will now sort out the positiveness of the term. And then if we're putting 3 in there, on the denominator we're going to be having of course r squareds from 1 to 3, so of course it's going to be 1 plus 4 plus 9. So I claim this is actually the general term of the series that we have up there. So let's write it on the top left because we will need it perhaps for later, and I'm going to use this board for doing all sorts of stuff. So this is to infinity, n is equal to 1, And inside the big sum, I have minus 1 to the power of n plus 1. And on the denominator, I have another sigma. And the sigma is r squared from r is equal to 1 to n. Okay, let's clear the board. So we have written that down. We have it now written, and we have also written it up there in compact form. So let's think now, what can we do with this particular quantity? Does it help us? I think it does, because of course this particular quantity is replaceable with the standard formula, which is in the formula booklet for most exam boards. So I'm going to put a vertical equal. So I'm coming down from this line and say, okay, without a shadow of a doubt, I can write this as replace just this denominator with the standard formula. You can look it up, of course, if you have forgotten. The sum of r squared is 1/6 n plus 1 to n plus 1. And to save me writing this again, just merely to deal with that 1/6, 1 divided by a 6 is of course a 6. So I can write this either there, or in fact probably better to move it in front of the sum. So whatever I'm trying to find is in fact 6 times something. What's my next step now from this particular line? There's a couple of things that come to my head, but they all lead to partial fractions. Method of differences perhaps, but definitely this particular denominator needs to split. So I'm going to do it on this line here, and just I'm going to do back cover up. We're on enrichment level now. You can of course do your partial fractions properly, take your time if you're unhappy with that, but I'm going to do it on the spot. So this is the 6 in here. I will explain what I'm doing. Just let me write it first of all. So this is from n is equal to 1 to infinity, and minus 1 to the n plus 1 with an n. What I'm writing at the moment is not correct, so please do not hurry me. I will explain, because of course what I'm writing now, it appears to be rubbish, and it is rubbish. N plus 1 over n plus 1, and we have the third item, which is going to be another plus 6 lots. Okay, now we'll explain what I'm going to do in here. I'm a little bit sloppy. I'm just doing too many things at once. But as I just explained, this is enrichment. You should be able to follow what I'm going to do next. I'm going to look at this sum, ignore the alternating sort of term here, and just break this bit here by cover up, and then write the numerators in each of these sums that are just split. So of course this is not necessarily, it might be a 2 there, a minus 3 to put in there after I do my partial fractions, and a 5 or whatever. So we're going to see now what these numbers are. I'm going to use a red pen for this. So I'm looking at this thing here. I'm ignoring this term here. I'm just treating it as being 1. So when n is equal to 0, so I'm going to fill in this sum now. When n is equal to 0, I'm going to get 1 over 1 times 1. So this is in fact 1. It's actually just like that, but I will put the 1 there just for reference, okay, from the partial fractions. My next line is when n is equal to minus 1, so I'm covering this one here. The answer is going to be 1 over minus 1 times another minus 1 now from this. So that's in fact also a 1. Okay. That doesn't look too good for method of differences, because of course for method of differences I require minuses. And let's see what the last fraction is going to have. In order to get rid of that, I need n is equal to minus a half. So that's going to be 1 over the 1 from there. What am I putting? Minus a half times positive half. So that's 1 over negative a quarter. So this one has in fact got a negative 4 in there. So this is now correctly split. I hope you follow what I've just done in there. For those who are still perhaps a little perplexed, all I've done is, I'm not going to do it of course now, I'm just going to show you very, very quickly. I took the partial fraction, I took this particular fraction and I broke it, and it turns out to be the following quantity. You can do, of course, your partial fractions separately and verify. It's not a 1, sorry, what am I writing? I'm doing stupid things sometimes. That should be a -4. Okay, and then I put them individually into sigmas with the 6 multiplier at the front, and of course the alternating terms. Okay, so far so good. Next thing I'm going to do, again, I'm avoiding writing too much stuff. These ones now we can just get rid of. We don't really need them there. I'll just put them there for reference. And also this -4, what we can do, so we don't have to just waste our time, is put a -24 in front of this sum and lose the -4 from here. So we have made some progress. The question now is, can we sum individually these 3 quantities? What are they? Okay, we're going to start from the first one, which probably is the simpler of the 3. Let's ignore the 6. The 6 does not really bother us in any way. Let's write a few terms to actually see what kind of things we're getting from this. When n is equal to 1, this is positive, so it starts with a positive term. The terms will alternate, but the first one is positive. 1 over 1, or just 1. The terms, as we said, they will alternate. Then it's going to be 2, a third, minus a quarter. Okay, interesting. We should know what this sum to infinity is, and if you don't, I think I have already done a lecture, but sometimes I'm uploading videos not necessarily in the order that are recorded. But I will tell you what, first of all, I'll tell you what that converges to. That in fact, the sum to infinity is the log of 2, and the way you can convince yourself it is, if you haven't seen this before, if you're unaware of this fact, if you take the Maclaurin expansion of 1 plus x, the log of 1 plus x, which it's in the formula booklet, and whatever it is not difficult, and put there x is equal to 1 on both sides of this expansion, you will get the expansion will turn into this, and of course when you're putting 1 in there, you're going to get log 2. That's where it's coming from. So in fact, this particular quantity, I can replace it and say, okay, fantastic, that is just simply, let's write the 6 as well so we don't forget it, it's 6 log 2. That's this bit here. Okay, let's look at the next one. That wasn't that bad. All right. So we generate some terms for this one also, in the hope that we might recognize it. It's very similar, isn't it? I mean, it's exactly the same thing, but we got this n plus 1. How does that change things? Okay, when we're putting n is equal to 1, we start with a positive term. So it alternates positive, negative. 1 over n is equal to 1, it starts with a half minus 1 over a third plus a quarter, I see. Okay, very annoying. So this is how we're going to do this particular one. Plus 1/6 minus ... Okay, let's call it S. It's probably the easiest way to see what that is. Remember this particular one, the well-known one, and let me just write it up here so you can actually see what I'm doing in there. 1 minus a half plus a third minus a quarter plus a fifth minus a sixth ... is equal to log of 2. Okay. This looks like it, but we got 2 problems. We got the signs reversed. If you look at the half here is positive, there's negative, and we're missing a term. We can easily sort these things out very, very easily. Multiply this line by negative, just to reverse the signs first of all. So that's, we'll sort one problem out. And then of course we're missing the 1 in there, no problem, add 1 to both sides. So 1 minus s is equal to 1 minus a half plus a third minus a quarter plus a fifth minus ... Okay, so what have we achieved there so far? Well, this particular bit is up there, it's log 2. So we're trying to find s. We're trying to find this thing here. So if we move the s to the left, sorry, to the right, I beg your pardon, s is going to be the one that we have in there minus log 2. So we have also obtained this particular one. It was related to the first sum. So we don't make a mistake. Don't forget the 6. So that is now this quantity here. And this is 6 lots of 1 minus log 2. In fact, the log 2's will cancel because we've got 6 log 2 there, minus 6 log 2. So these two sigmas together just add up to 6. The question now is, what is that last item? If we do that, we're done. This doesn't look pleasant at all. Let's generate a few terms in the hope we might recognize something. The 24 again does not bother us. It's just a multiplicative constant at the front. In fact, minus 24. I'm going to look at this and just try to think, can I relate it to anything known? N is equal to 1. Again, it starts with positive. And it will alternate. That's like an alternating quantity. When n is equal to 1, it starts with a third, and then it goes to minus a fifth, plus 1/7, minus a ninth, and so on. It has a pattern, but it's not a pattern that we can just say, okay, I know what this converges to. A long time ago, I think I used to know a lot more serious standard results purely from having done them many times. And I think there is actually, I think that probably has pies. But I can't quite remember. Of course, I'm missing a few bits at the front, but I could be wrong, in fact. So maybe it's not pies. So how are we going to come up with this particular one? Of course, not geometric. This is what I'm thinking in this particular for this particular one. I'm thinking of two quantities. Two quantities come to my head. That's why I just threw out the term pi. Arc sine comes to my head, and arctan. And I will justify why I'm thinking of these two quantities when I'm looking at this. Both of these items are, well, these functions rather, they're both odd. So their expansion, so though I don't know them by heart, and I don't know if they're actually given in formula booklets, will have odd powers. They'll be sort of x cubed and x to the 5, and things like that, because these are odd functions. And I think, I've got a feeling they both alternate. They both have plus and minuses. I don't remember, but I'm going to have a go at it. So I'm going to start with the arctan because it's probably easier. So if I hit a brick wall, I haven't lost too much time. Well, if I hit a brick wall with the arc sign, I would have wasted too much time. So I'll explain to you what I'm going to do. Okay. Let's write it here. And in order to find the expansion of the arctan, to just see if I'm on the right track, I'm not going to start with the arctan. I'm not going to get any Maclaurens, anything like that. I'm going to start bizarrely from this quantity here. Okay, why that for an arctan? Because clearly this integrates to an arctan. So I'm going to cut a lot of the work out. And of course you ought to know, I don't think I need that up here. These are standard little tricks and little tools that you must know. 1 minus x is, of course, this quantity here. And if you have it with a plus, very powerful tools. You use them all the time when it comes to serious and many other places. Okay, very, very important. Just binomial expansion, you can think of them as sums to infinity of geometric progressions, or you can do the binomial expansion. So if we know these facts, to actually do the expansion of 1 plus x squared is dead easy. It's just that instead of an x, we have an x squared. So it's, of course, alternating terms but it's going to be 1 minus x squared plus x to the 4. And you will see what's going on a little bit with that. I hope it's the one that works, because it's plus minus there. It's not, the arc sign is a lot harder. X to the 6 plus x to the 8 and so on. Okay, so when I'm going to integrate this now, both sides of this particular equation with respect to x, I can do indefinite integration, but I think probably, because of course this will integrate to an x minus a third x cubed plus a fifth x to the 5, so it produces the right quantities, and I would like to deal is substituting there 1. So let me put the limits. If you're not following quite what I'm doing, you will see when I do a couple of lines what's going on a little bit. I could put constants plus c and then work out my constant, but it's probably easier to integrate between 0 and 1. And let's see what happens. This of course integrates to arctan, the arctan of x between the limits of course of 0 and 1. And the right hand side is very easy. It's of course term by term x minus a third x cubed, not minus, yes, sorry, I'm looking at the wrong thing, I was gonna miss a term by mistake, plus 1/5 x to the 5 minus 1/7 x to the 7 plus dot 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 between the limits of 0 and 1. And I did rub off what this thing was. I have to redo it so you can actually see what's going on. I'm just gonna put it here and rub it off afterwards. This particular one, forget about the minus 24, it was alternating terms, so that's 1 over positive is a third minus a fifth plus a seventh minus a ninth and so on. So what motivates me to do what I've just done there is if I put now in this particular line, first of all, if you look, that's why I put 0 there. If we put 0 there, this all just dies. But if we're putting ones, we're gonna get 1 minus a third plus a fifth minus a seventh and so on. So we're getting something which looks like that, but the looks of things is not quite the same. We're out by some bits and bobs. Let's go to the next line and see what we're missing. Well, the arctan of x, evaluate at 1, it will give you pi over 4. And evaluate at 0, the arctan of 0 is of course 0. So that's pi over 4 is equal to, we're putting of course the bottom limit will produce nothing, and it's just the 1 substituted in there, so it's going to be 1 minus a third plus a fifth minus a seventh and so on. And I think this will work because I'm going to rub off the 2 lines above it, and we're going to do a similar trick to what we've done for this particular one. I think it will work. Let me just check it. This is equal to pi over 4. Let me just write the pi over 4 on this side because I want to stand on that side of the board and I will be blocking what I'm doing if I write it like this. Let's look at, this is what we're trying to get and this is what we got. Okay. First of all, we can actually subtract the 1 to the other side. So I'm looking at this line here and say minus a third plus a fifth minus a seventh plus a ninth minus 1/11 and so on from this line here is quite clearly going to be equal to pi over 4 minus a 1. Okay. The next thing that I want to do is I would like to reverse the signs on this, because if I look at this the wrong way around, so clearly 1/3, perhaps I should have actually done the other way around. I'm very stupid in fact. Let me just write again because actually I'm going to be writing a lot more. I didn't actually realize actually better to do something else. You see, this is the bits that I want to move to the right hand side, so I can actually say 1/3 to the right minus a fifth plus a 7th minus a 9th and so on. So I'm taking this to the right, is clearly going to be the 1 minus the pi over 4. So this is what I've got in there. And that is it, isn't it? Because, of course, that's my series. And therefore, this particular sum, the final one, okay, is going to be equal to, I'm going to write it on the side here, is, let's not forget the minus 24 at the front of the sigma, lots of 1 minus pi over 4. Okay. Hope I haven't made any mistakes, and let's put all things together and hopefully come up with an answer, a sensible answer for this particular sum. So the final answer to my problem is going to be equal to, I've summed them individually, so I've got the 6 log 2 plus, I'm going to multiply this bracket, 6 minus 6 log 2, although I did mention earlier on these things would have cancelled, I could see this. And the final thing that I've got from there is going to be minus 24 from multiplying the bracket plus 6 pi. And this, of course, when I tidy all of this up, it should give me 6 pi minus 18. Of course, that 6, I can factorize it out, but I think that's good enough to just leave it as it is. I hope you follow what I've just done. I hope I haven't made any mistakes in here. There was quite a lot of stuff and very, very different ideas, but all further maths, nothing exceptional, nothing extraordinary in all of this. And on that note, who's laughing now? I think we're done.